Okay, guys, I'm recording this lesson today because I'm not sure how far we're going to get. It's 9:34. We have till 9:50. We can probably squeeze this in. I didn't get this all in my first period class, so I'm going to record this. So if you have any trouble understanding anything on this lesson, you can always go back and play it back. I'll post it online. So what we're moving from now is we're moving away from the identities where we have, an equation where we have the left side equals the right side and it's true for any value of x. Now we're moving back towards solving equations where there's 1 or 2 or 3 or maybe 4 answers that make the equation true. So we're solving for x that way. And when we do that, we're going to solve trig equations using the same kinds of strategies that you used back in Algebra 2 when you were solving algebraic equations. So we're going to do things like isolate the trig function. Okay, that's the same thing as like isolating the variable in an algebra equation. We're going to sometimes combine like terms. Sometimes we're going to factor. Sometimes we're going to square both sides of the equation. Sometimes we're going to need to use the quadratic formula. Only we're going to apply all of this stuff to equations that involve sine, cosine, tangent, that sort of thing. So in addition to that, with the trig equations, we're going to also add the strategies that you learned for the trig identities. We might, combine like terms. We might replace some terms with a trig identity, things like that. So when we solve a trig equation, there's 3 fundamental questions that we want to address, and we're going to take these a day at a time. Today, the fundamental question is, are the trig functions the same? So in an equation, is everything written in terms of sine x? Or is everything written in terms of tangent x? If that's true, then there's a certain methodology that we'll use to help us solve those equations. And then we'll address the other 2 equations next week. So let me scroll up here to the examples for today. Get rid of my little cloud. There we go. All right, so our first equation, our first problem here is 2 sine x minus root 3 equals 0. I guess I'll leave it right there. Good. And the domain here is 0 to 2 pi. So we look at the equation and we ask ourselves a question, are all the trig functions the same? Is there more, just one trig function? In this case, yes, there's only one trig function in the equation. So if you were solving this algebraically you would have, if you had like 2a minus root 3 equals 0, if I was trying to solve that, I would add root 3 to the other side of the equation, and I would divide by 2, and then I've essentially isolated the variable. So I'm going to do the same thing, only this time there's a sine x. The sine x I'm going to treat as my variable. So as I work through this problem here, I'm going to add root 3 to both sides of the equation. So I have 2 sine x equals root 3, and then I'm going to divide by 2. I get sine x equals root 3 over 2. So now I want to find out, what are the angles? What are the x values? And in this domain, what are the x's between 0 and 2 pi that have a sign that's root 3 over 2? What? Pi over 3 is one of them. That's right. How'd you do that?
Well, you make 60 degrees. Because if you just make the triangle, and it's either 30 degrees, it's either 30 or 60 degrees, and 30 degrees has 1 over 2, and 60 degrees has 2 over 2.
Okay, so the key here was making the triangle, okay? And Mark did that in his head, but we can certainly write this out, and I want to write it out because there's actually more than one solution. If we draw the triangle, and this goes back to reference triangles that you learned back in chapter 4. What you're going to notice today is we're going to pull in all of the skills pretty much that you've learned for trig ever since we started. We're going to pull it all together today. We're going to need a lot of different things. So we're going to need reference triangles for one thing. So I want you to remember, if you remember that little graphic that we used, it was all students take calculus. This tells us where the trig functions are positive. Trig functions are positive. So in the first quadrant, all of your trig functions are positive. In the second quadrant, just the sine. In the third quadrant, just the tangent. In the fourth quadrant, just the cosine. So when I see a positive value here, if I see root 3 over 2, that means I'm going to draw the reference triangles in quadrants 1 and 2, because sine is positive in quadrant 1 and sine is positive in quadrant 2. So I'm going to draw these triangles, remembering that a sine ratio is the opposite over the hypotenuse. Okay, opposite over hypotenuse for sine. So the opposite side is going to be root 3. The hypotenuse is 2. I'm going to draw that same triangle over here in quadrant 2. The opposite side is root 3. The hypotenuse is 2. All right, so the next thing we have to recall is our ratios for a 30, 60, 90 triangle. So we're going to pull that back. That was one of the first things we learned. So I go back to thinking about my 30, 60, 90 triangle. Here's 30 degrees, here's 60 degrees. I remember the ratios are 1 to root 3. And remembering that 1 is opposite the smallest angle, so smallest angle, smallest side. 2 is the longest side of the triangle, opposite the largest angle, 90 degrees. And then root 3 is kind of the middle size side, that's 1.7 approximately, across from 60 degrees. So from recalling this 30, 60, 90 triangle, I know that's a 60-degree angle, that's a 60-degree angle, and now I have to name those two solutions. So here's one solution, so relative to 0 degrees, there's one solution, that's x equals 60 degrees. Here's another solution, that's x equals 120 degrees. And then I want to take note that my original domain was 0 to 2 pi. So if x is, the domain is given in radians, I'm going to give my answer in radians. So I'm going to convert this to pi over 3 and 2 pi over 3. So there's another concept that we learned early on, how to convert from degrees to radians. Right? If you've forgotten, you're going to multiply by pi over 180 degrees. Multiply by pi over 180 degrees. Or think about dividing up this, dividing up, going around the quadrants. If I go from 0 to pi, that's 3/3 pi. 60 degrees is 1/3 of the way. 120 is 2/3 of the way. So this is 1/3 pi, and this is 2/3 pi. So you can kind of cut your way around. All right, so that's the first problem. The next problem looks just like what we did with the identities. So that's why I wrote this on the board. 2 sine squared x plus 3 cosine x minus 3. That factors to this expression right here. So when we look at this problem and ask ourselves the question, are all of the trig functions the same? The answer is no. And the solution is, then let's make them the same. Okay, and that's what we did with this problem with the identities. So from the previous example, this becomes 2 cosine x minus 1 times 1 minus cosine x. And when you go home and you rewatch the video and you're trying to figure out what's this dot, 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 where did this come from, remember that's from the previous video. It's all explained there. And I'll have that posted as well. Okay, so when you solve algebraic equations, you're often, you're often factoring and setting the factors equal to 0. So same thing here. Once we get it in factored form, I'm going to set those factors equal to 0. So I have 2 cosine x minus 1 is 0, and I have 1 minus cosine x equals 0. And then I'm going to solve for cosine x. Here, cosine x is equal to, when I add 1 and divide by 2, I get a half. Here, cosine x is equal to positive 1. To figure out the angles where the cosine is a half, I need to draw a reference triangle. So here's my axes. I'm going to draw the reference triangle where cosine is positive. cosine is positive in the first and fourth quadrants. So I'm going to draw a triangle such that the adjacent side is 1 and the hypotenuse is 2. And I'm going to draw that same triangle in the fourth quadrant where cosine is positive, so that the adjacent side is 1 and the hypotenuse is 2. Again, you recognize those as 30, 60, 90 triangles, so this is your 60-degree angle. And then we're going to name those. This domain is also given in radians. This is from 0 to, that's a 2 pi right there, we're kind of missing. So when I name these angles in radians, this angle right here, x equals pi over 3. And then to name this angle, all the way around would be 2 pi or 6 pi thirds. If I take away 1/3 pi, that leaves me with 5 pi over 3. Or if it helps you, can kind of count your way around in thirds. I know that if I was kind of counting my way around, this would be 1/3, 2/3, this brings me to 3/3, and then 4/3, 5/3 pi. So that's how I name that. Two solutions are coming from a reference triangle. This other solution now comes from the unit circle. So now we're pulling in yet another concept. We're going to pull in the unit circle. I remember that I have to do the unit circle because if I try to write this as a ratio of 1 over 1, I can't have the adjacent side over the hypotenuse be in a ratio of 1 to 1 because the hypotenuse always has to be bigger than the legs. So I can't possibly make a triangle, it just won't work. So use your unit circle, remembering that this, the horizontal axis represents the cosine, the vertical axis represents the sine, and so the first coordinate is the cosine, the second coordinate is the sine, and so I want to know where is the first coordinate equal to 1. The only place on the unit circle where this first coordinate is 1 is at 0. So x equals 0, and then again at x equals 2 pi when we rotate around. So we've got those 4 solutions to our problem. All right. Let's take a look. Yes, questions. Let me stop for a minute. Go ahead, Michael.
Are you, in these questions, are you solving for the sine of x or are you solving for the x?
Solving for x. Solving for x. I want to know what's the angle that has a cosine of 1/2. The cosine of this angle is 1/2. I want to know what is that angle. All right, let's go to the next page. And, what's that? If the domain is given in radians, then the answer should be in radians. If the domain, these happen to be that way. If the domain is given in degrees, then give your answer in degrees. Okay? All right, this next problem, if you look at this, everything's kind of different. There's, you know, a lot of different trig functions there. So we want to kind of simplify this if we can. So this is where all your work with identities comes into play. I would look at this and I would say, well, this is the same thing as sine x plus cosine x times cosine over sine. I might want to combine those fractions. And when I combine those fractions, the denominator is sine x. So multiplying this first fraction by sine x over sine x, that's going to give me sine squared x plus cosine squared x. And that's always a good thing because that means my numerator is now 1. Okay? So now I've got 1 over sine x, and that equals 2. And now, by your rules for proportions, we can just flip that proportion, and we can write this as sine x over 1 equals 1/2. If 1 over sine equals 2 over 1, then sine over 1 equals 1/2. And now we can just solve with a reference triangle. Yes?
When you started at the very beginning,
Yes.
in order to add those, don't they have to be equal?
They need a common denominator. And that's what I did right here. I multiplied sine times sine to get sine squared, multiplied sine times 1 to get sine. So this was now sine squared over sine plus cosine squared over sine. I had a common denominator. I multiplied by sine over sine.
Where did you get the cosine squared x?
Right here, cosine times, because this is cosine times cosine over sine.
Oh, it looked like it's subtraction.
Yeah, no, it's multiplying, it's multiplying. Okay, so now if I have sine x equals a half, I'm going to write my reference triangles in the first and second quadrants. That's where sine is positive. I need the opposite side again. This is sine, so opposite over hypotenuse. Opposite side is 1, hypotenuse is 2. Opposite side is 1, hypotenuse is 2. Again, hopefully you recognize those as 30, 60, 90 triangles. And this angle right here is x equals 30 degrees, which is pi over 6. And then the other one is 5 pi over 6, or 150 degrees. So there's our solutions. Okay, one more problem. With this one, the temptation is to divide by tangent x. What I want you to realize is that if you divide by a variable, you're actually losing a solution, okay? If you had a problem like a cubed equals 3a, if I simply divide both sides by a, then I have a squared equals 3, and I would get a equals plus or minus square root 3. You guys follow that? Two solutions. All right, now, instead, if I take this a cubed equals 3a, instead I'm going to subtract and then factor. If I subtract, I have a cubed equals, or excuse me, a cubed minus 3a equals 0. Factor out the a, and I have a squared minus 3. And now when I set these equal to 0, I get a equals 0 or a equals plus or minus root 3. So notice when I divided out the a, I only got the plus and minus root 3 as my solutions. When I subtract and factor, I still have the a equals 0 as a solution. So don't divide by variables. Don't divide out trig functions because you're going to lose one of your solutions. So kind of taking that knowledge to this problem, I'm going to now write this as tangent cubed x minus 3 tangent x equals 0. So I did a subtraction, and now I'm going to factor. And I'll erase this just to make a little space here. That was a little algebra lesson as a reminder. We need lots of algebra reminders. So now let's factor. Now I have tangent x as my common factor, and that leaves me with tangent squared x minus 1. And now when I factor that, I have tangent, oh, I lost the 3. Yeah, thank you. I knew that was coming. There we go. So tangent x times, this is going to be tangent, actually I'll just leave this. I think what I'll do right here, I'm just going to set it equal to 0. Hold on guys, we still have like 2 minutes. We have tangent x equals 0, or tangent squared x equals 3. So now when we finish solving, when I take the square root of both sides of the equation, I have tangent x equals plus or minus root 3. All right, this is going to give us a lot of solutions, so I want you to see this. When you look at tangent x is positive root 3, we're really talking about tangent x equals root 3 over 1. And when it's negative, we have tangent x equals negative root 3 over 1. Tangent is positive in quadrants 1 and 2. So we're going to draw our reference triangle so that we have opposite over adjacent. This is root 3 over 1. Down here, the tangent is positive because it's negative root 3 over negative 1. Tangent is also positive in the second and fourth quadrant. So now I have two more triangles to draw. Opposite, so we'll make this positive root 3 over the negative 1. And then down here, I have negative root 3 over the positive 1. So that's a lot of solutions. It all comes because we took the plus or minus square root. So now I have to name all of those, okay? This angle is pi over 3, so x is going to be equal to pi over 3. This angle here, hold on. Right here we have 2 pi over 3. Right here we have 4 pi over 3. Hold on. And right here we have 5 pi over 3. Still have to use your unit circle to find this solution, okay? All right, you guys can go. See you.